Now for butane, same thing. Now you have got two methyl groups here that will bounce off each other and interact not so well. If you look through the carbon 2 and carbon 3, what happens is you get this drawing for the Newman projection, and the methyl group, there are two kinds of conformer. We have the anti-conformer and we have the gauge conformer later on. So anti means that you're putting these two biggest group on the opposite end. Now what happens is, let's say the green ball here you see in this molecule are the methyl group. Okay, so if I put them on the opposite side, you see top and bottom exactly 180 degrees, it means that they are anti means opposite. Now as I rotate, right, I'll get an eclipse. Again, it's very bad, so bad. And I rotate again. What happens now with the green balls? They are the methyl groups. They are much closer together, so they are at 60 degrees, and we call this a gauge conformer. Okay, gauge, German word. So with these, they are closer together, experience a higher strain, more energy, and less stable. So in general, we have steric strain, and the term the repulsive interaction within a molecule when two groups are too close, okay, then their atomic radii allow. Right, as you rotate this butane molecule, you see the transformation from the butane gauge conformer to the butane eclipse conformer, and of course, eclipse always has a higher energy than the staggered conformer. Okay, under staggered you have gauge and anti, and gauge is higher energy than the anti. So over here you see that it is a cylindrical ups and down again, but no longer sine graph or cosine graph, because we have a conformer that's the most stable, which is staggered and anti. We have something that's also staggered, but it's gauge, but gauge has a slightly higher energy than anti, because the two big groups are closer than over here. What's not stable will be your eclipse. Eclipse is always having very high energy. You see this maxima. However, there'll be one that's even worse, where the two methyl groups are exactly eclipsing each other. So this table here will give you a summary of what's the energy cost when you have different kinds of interaction in the conformer, okay, and what are the causes: torsional strain, steric strain, etc. Okay. Again, you do not have to memorize these numbers here, because it's stated primarily as a reference for you to understand the logic behind. So let's see this molecule here called decane. Decane means you have an alkane with 10 carbons. So the most stable alkane conformation within the decane will be the carbon-carbon bonds are anti with each other. So it's up, down, up, down, up, down. You see the drawing in 3D. The hash bonds over here means going to the back. This is a wedge bond, means going to you. So is it in, out, in, out, in, out, okay? They will not eclipse each other. At room temperature, the rotation of the sigma bond occurs very rapidly. It doesn't mean that, right, you will only find decane any temperature and pressure at the same conformer. No, because it has energy. It can still rotate. So the rotation of the bonds will occur all the time, and it's all at equilibrium. However, there will be more proportion of molecules that will be present in the more stable conformer than the less stable one, because it's of a lower energy. So lastly, some practice for you. Drawing Newman projection. You have to be very good at this. So sight along the C1, C2 bond of a 1-chloropropane and draw the Newman projection of the most stable and least stable conformer. I will go through with you in class with respect to the answer. See you!